and try and remember how to do this. I have no idea where the closed caption option went. Okay, I have no idea where the closed caption option went, so we're not using it, I guess. Okay, unless you see it. Am I closed captioning?
You are not.
Well, it used to be here. Okay, so that's the end of that. What is this? Live transcript. Ah, okay. So closed captioning is now called live transcript. Okay, do you see it now?
Yes.
Okay. Let's start with review.
So, kind of review threads. They basically say, all right, now use a bit of the processing power and run this code, this function. Is there, like, what is the amount of processing power that it uses? Is there like a certain amount?
Interesting question. There is no predefined limit. So just as there's no predefined limit on how much of the CPU an application can hog, there's no predefined limit on what a thread can hog. There are ways to limit the amount of processing power applications and threads can use, but none exist by default.
I have a question.
Yeah, go ahead.
For the get opt, in the example you gave us over GitHub, you list a default state. How does that necessarily work, and what would the default state for our get opt be for this project?
Okay, well, the best way to do that is to look at the code. So let me fire up and edit. What the hell? All right, let me fire up code. And then let's go look at code. What?
We can't see a screen if you're showing it.
I'm not showing it yet, but thank you for the reminder. All right, where am I? So. Unfortunately, I started organizing all my code and now I can't find anything.
We all know that feeling.
Yeah. What am I going for? Get out, right? EF G. Okay. Okay. So this is a very complete example, and it has the code to implement defaults. So here's an integer, which will have a default value of 17. Here's a float that has a default value of 1, 2, 3, 4, 5. Okay. So your arguments, command line arguments, will be housed in variables. So if the variable has a default value by giving it an assigned value, if the option that drives that variable isn't given by you, then it won't be changed. It'll still be the default. So
So
here I
for-
put 1, 2, 3, 4, 5 in a float. And if you look at the code that handles the options, if the F is not given, this line will not be executed. Therefore, the value of a float will still be 12.345. Got it, Thomas? Okay. Now, the next question is, how do you handle a required option? Okay, so suppose in this case, the -S option is required, and I document that here. That's the help string, the help document, help text. So if it's required, then all you do is your switch statement in the while loop looks the same as any other, but you put in some kind of code that checks to see if that option was indeed provided. So in my case, I'm getting a string. The string starts out as empty. So if the string size is not greater than 0, the option wasn't given. So I'll return a false here, which says a required option wasn't given. Okay. So here are the basics of get_opt. First, you have to include it. You have to include it. You cannot get_opt for Windows. It is a big horror show to get_opt for Windows. Don't ask me why, but Windows does not come with get_opt, nor is there a get_opt replacement that's trivial to get. Instead, you have to go hunting for it. So if you're going to use get_opt, do it on the Mac, or do it in the terminal on the Mac, or do it in Whizzle on Windows. So you have to include it.
About those
Yeah.
poor people who have to use VS Code.
Well, the poor people have to use Visual Studio, et cetera, right?
I'm wondering why. It doesn't look like it would use anything OS specific. It's just
Who
string
knows?
stuff.
Yeah, who knows? But a version for Windows does exist. You just have to look for it. All right, now get_opt is going to process the arguments to main, because those are the command line arguments. So as you'll see, where I call get_opt, I pass in argc and argv. Then there's a specification of what arguments, command line options you want to process. So a letter, each one of these letters represents a command line option that I'm going to understand. Now, the only difference is the letter followed by a colon or not? So if the letter, in this case F, is followed by a colon, it means that when the -F option is given, it must be followed by an argument. Okay, now look at the H. So when -H is given, it is not followed by an argument. All right, so let's take a look and run these. Let's see, do that. Boy, that's awfully tall. And that's awfully slow. I haven't used this. Well, let's see what happens when I do that. Oh, okay. Okay, so I just ran it with no options at all, command line arguments of any kind, and it printed the help. So how did that happen? So while an integer C is the result of get_opt, while that's not -1. So when getup returns -1, the while loop is over. There's the default is dropping through to -h. Okay, and also I've got code here. Where's main? I have no idea where main is. Okay, there's main. So if the options fail, handle options fail, it prints the usage. So there you go. So let's take a look at -h. So here's the handler for -h. All it's going to do is return false, which the code that called this takes. If it's false, that means print the usage and exit. But let's take a look at B. So -B is an optional setting of a Boolean. So notice there's no colon here. So the action of the -B is invoked just by its presence. So if you say -B, a Boolean is true. It gets set to true. Compare that to, let's say, C. C has a colon after it, which says that if the C option is given, it must be followed by an argument. So let's try this, and I'm sorry, I got to get rid of this. I can't see my screen when this stupid live transcript is on. So sorry, it's going
There's
away.
a button to hide subtitles, by the way.
There's a button to hide the subtitles.
Yes.
Okay. I'll turn
When
it
you
on
click on
again.
live
Yeah.
transcript next to record, you can
Got it.
press hide
Okay.
subtitles.
So I'm confirm for me, please. The subtitles are still on.
Those are on a individual by individual basis.
Okay. Can someone verify that the subtitles are working?
I can confirm.
Thank you. All right. So a.out/-b. And why did this do what it did? I have no idea why the program is behaving in this way. This program has been working for years. So it did not recognize -f, and it did not recognize.
No, you already compiled it, I have a feeling.
All right, well, let me. Oh, the problem is -s is required. Duh. Okay, so so there's the float argument will be 12 -s. Here is your goddamn string. Okay, there we go. Okay, so the float came down here. The integer option -I wasn't given, so it has the default value. Okay, anybody have any questions about how getup works? Okay,
I was going to ask.
go ahead.
I was going to ask about what if we do not include a case? Would that just mean it goes to the default that you have set up before?
A case.
Say when you call get opt use through the command line, you don't have I or B or C or yada yada.
Well, if it is here, if the letter you're saying you didn't specify is part of that option string, then the switch statement missing the case would mean that it would go to the default.
Okay, so it's just, and my question is like the word default within switch just means it doesn't do anything.
You've not seen that before?
No, we have not used a switch before until now.
Really? Jordan, you haven't used a switch statement?
I have, but I'm pretty sure I learned it separately in my own travels.
All right.
I thought we learned it in like CS2 or something. I seem to remember using it.
I think it was in a Xi books for my CS1, but that was like the only time I formally learned it outside of
Okay.
using it. In
All
my
right. Well, a switch statement in C and C++ can switch upon any integer type. So it can switch on int, on short, on char, on long, but that's it. That's the only thing you can switch upon. And the case says if the value that you're switching upon is the letter H, you'll do this. Well, that's straightforward. The two things to know in addition is that if you don't have a break statement in a case, the code will drop down into the next case. Okay, Thomas, you got that? All right.
Question.
Yeah, go ahead.
I'm just a bit confused in that string in the while statement where it's checking argv for the amount of argc. I'm just confused as to what the colons mean and how the colons are used there.
Do you mean here?
Mhm.
Okay, so when you call getopt, you have to give it your arguments. So that's why this is here. And just screwed that up. Okay, but then you also have to tell it what command line options you're interested in defining. And that is this string here. So each letter corresponds to a command line argument that you're going to process, command line option. And if the letter is followed by a colon, it means that on the command line, it must be accompanied by an additional option. So for instance, F has a colon, but B does not. So I can say a.out dash B, and I got to give it the goddamn dash S. Okay, so the Boolean is set to true because dash B was present. Now I will eliminate the dash B and it will print as a 0.
Okay, I 100% understand now.
Okay.
Yep. It just means like there's an accompanying value that references to the option itself.
Right, that comes after the option itself.
Okay.
Right. Now, the way that you get access to the options that come after a letter that has a colon with it is using opt-arg. And that is a C string that is defined by the getopt package. So you notice that if I need a value other than a C string, I have to cast it. So here the C string is converted to a C++ string. Here the C string is converted to a float. Right, so all of these options, opt-arg is a C string, pointer to char star. And once again, if not talking about not getopt, but talking about switch, if a break statement is missing, if I fell into the C case and the break was missing, I would then drop into the S case. So the break causes the switch to end there and go to the statement beyond the switch. This is the other place where the break statement can be used. The break statement can only appear inside of a loop and a switch. The continue statement can only appear inside a loop. Okay, any questions about getopt?
Yeah, so the string that you supply into the getOp function, are those letters customizable, or do they have to be every single time I ever use getOp, they have to be those?
It can be anything you want. Okay, so the author of the program writes, whoever's working on the options for the program will manipulate that string.
Do they have to be, do each, like, what's the word? Does each command have to be one letter, or could it be like a word?
There is a way to do what's called long options, but I'm not going over that.
Fair enough.
So long options will typically look like, what's a program that I can easily get to? Well, long options would typically look like this: dash, dash, enable float. Okay, so long options typically start with dash, dash. And they exist in parallel with short options. Okay? But I haven't shown you how to use long options. For anybody who programs in Python, Python has a wonderful getopt as well that makes it very easy to use long options. Let me show you. Okay. Major minors, okay. So looking down here, so here's my help usage for this Python program. A dash C is the same as dash dash churn by month. That's the long option. And that is handled here. So you give it getopt with all of your argv values from number 1 to the end, and the short options and the long options. And then you'll have a loop and what amounts to a switch statement. And it says if the option was the short one, or if the option was the long one. So that is the theory behind working with long options. Is that okay, Jordan?
Yeah, thank you.
You're quite welcome. I'm running an editor inside of an editor. Okay, any other questions about getopt? You use it in a loop. And it's while an integer is not -1. When the returned value is -1, the loop should exit because there are no more options. So is there anything else to learn from here? So once again, an option that has a default value simply means there's a variable somewhere that was assigned a value before getopt was invoked. And if the option is present and given by the user, the new value will overwrite the old value, and that's how you get a default value. Second, if an option is to be a required option, you have to implement the check yourself to make sure it was given. Okay? All right, now let's see how getopt is used in the current project. which I think I will just do, close that folder and open another folder. Almost there. I don't know why I just didn't go to the web, but anyway, so these are the command line options you must implement. -H, -S, followed by an integer, which sets the size of the arrays to be used in P5. -I, followed by an integer, which sets the number of iterations. So let's review this project. Does anybody have questions about this project? Okay. You are going to be, what is this project? You're given this implementation that uses a single core, and its inputs are a pointer to an array of floats A, pointer to an array of floats B, and the output will go into an array of float C. You're also told the size. The size is the same for A, B, and C. Your job is to time the performance of several implementations of this function. This is the single core without the neon instruction set. Each time through the loop, it will add 16 instances of A and B, creating 16 instances of C. That's what it does. Does anybody have any question about this code?
Could I ask a question just in reference to the project?
Well, we're going over the project, so now's the perfect
I
time.
mean, it's not about single core. I was trying to look up information about using get time of day because there's a lot of different like struct and data
Mhm.
types that I don't really understand what I'm taking from get time of day because you use a reference to like a separate TM struct and then you use
Mhm.
that to you parse that into a different format to understand like the exact time of day as opposed to seconds. So I was just wondering if maybe you would go over it a little bit.
Okay, I'm showing you two different ways of doing high precision timing. The first one is here. The idea is given, the theory of operation is given here. You capture the current time, you do whatever it is that you want to time. After you've done whatever it is that you want to time, you capture the time again, do a subtraction from the time now at the end minus the time from before, because the time from before is a smaller value. So you subtract now minus the time of the start. And what you get when you do that subtraction is an elapsed time. Okay, so get time of day. What the hell? If I double click on that, it goes bananas. Okay, so get time of day and you give it a time struct. And so I'm capturing the time at the beginning and the time at the end. And I use timer sub to do the elapsed time. Now you'll notice I say I'm specifically not completing the calculation. You need to look it up. Now, Nathan, you just asked, okay, that part where I want you to look it up, explain it to me. So what do I do? Do I explain it to you or do I have you look it up?
In fairness, there is awkwardly slim documentation on these things. I don't know why, but I had a reasonably difficult time of figuring out
It's
and
not.
finding
in my,
resources
it's not in my
on how to do that.
devdocs.io.
Okay, there's more than one person talking. Okay, Nathan?
I was just gonna say it's not in my normal reference where I go to for C and C++ implementation. I go to a website called devdocs.io that has an entire library of commands, and get time of day wasn't listed on there. So then I looked on the Linux Man 7 manual, and I was still just having some issues just understanding exactly what piece of it I was looking for. But this makes more sense now, showing me that you would use that reference start and the reference end and then timer sub, both of those. That makes more sense.
Okay, so here, I'm glad, but this was just man, get time of day.
Yeah, this is what I was looking at.
And what you'll see is that a time val is broken up into two longs, but you should use time t and seconds t, SU seconds t. So this value, TV sec, is the time, the elapsed time in seconds. So that's going to be an integer number of seconds. You have to add to it the TV usec after an appropriate division, because this integer represents microseconds. Okay?
I'm guessing we wouldn't want to use srand time parentheses 0.
Well, we're not using the, we are using the random number generator, but I think that's part of the program, yeah. I mean, what's the difference? Why does that matter, Thomas?
It's what I have compared to what you're explaining.
Well, the srand, when you call srand, you're giving it a null, so you're telling it not to fill in anything. It just does a return value. So let's do, what is the return value of get time of day?
It's an int.
All right. So, oh no, you don't call
Return
get
it.
time of day. You don't call get. You got me confused there, Thomas. You don't call get time of day for srand. You call time.
That's what I
Time's a
did.
different. Yeah, the time's a different function altogether. Okay,
And all it returns is a 0 or a -1, which is
that's
odd.
what get time of day returns. Okay, so man to.
Actually, it says both of them do.
Okay, this is a different function, Thomas. On return, on success, the value of time in seconds since the past epoch. Okay, that's completely different than get time of day. Question?
What is the type of time t?
You're welcome to look it up, but let's see.
It's got to
if we
be
go
pretty
here.
big, right?
Okay, so time val includes a time t, and I just mentioned that it was some kind of integer. So time t is going to be an unsigned long, I'll bet you. Okay. All right. Any more questions about get opt? Any more questions about timing? This is only the first way that I'm showing you to time. P6 also uses timing, but you'll use the modern way. Okay? The modern way is implemented through a platform independent C++ include. called Chrono. All right, so in this program, this is P5. I can show you, I think what I'm going to do though is demonstrate P5 on my ARM machine. So let me stop sharing. Let me start sharing from a different computer. Okay, so when your program is finished, this is what it's going to produce. In your ARM machine, let's run it with no arguments. Okay, so in your ARM machine, you probably won't have 8 cores. If you're running the VM, you should have 2 cores. So it'll be a 2 that's printed there. And the default value for the array size is 128. So let's ramp that up. -S, let's say 100,000. So there's 100,000. Okay, so there's the timing. That was run once. Let's get it to run 100 times and print the average. -I 100. Okay, so there it did the calculation 100 times and was real fast, and there's the answer. Now, if you want to see that running, go ahead.
I was going to ask, for when it comes to rounding the input for S, if it's, say, 17, would we want to round up to 32 or round down to 16?
No, you round up. Yeah, you
Okay,
always round
good.
up, because let's say you gave a value of 5. If you round down, you go to 0.
And we'd want to use the remainder function to see if it's equal to 0. Because that means it's divisible perfectly by 16 and has no remainder.
There are a lot of ways of doing that.
Fair enough.
So I did it using an AND. You could use it using mod. Remember, if you were writing mod assembly language, the ARM doesn't have a mod instruction. So mod turns into like 3 instructions, 4 instructions. Okay, since I want to make sure it's a power of 2, I can just use AND. And that works only because it's a power of 2, 16.
According to Wikipedia, in most POSIX systems, it's represented as a 32 or 64-bit signed integer, which makes no sense to me.
Well, I suppose if it's signed, you're talking about time t or
Yeah.
you know, well, if it's signed, that means you can represent time in the past.
Yeah,
Okay,
but
who
it
cares?
also means you'll run out pretty quickly of numbers for seconds.
Well, now it's a long, so it works better. In the old days, it wasn't a long, and you had a problem. Number of seconds since 1970, that's when the epoch began, ran out a long time ago as 32-bit number.
What are we going to do when we do run out after the epic or epoch?
You mean after we overflow a 64-bit number?
Yeah. Are there any like plans for that? Because I know that's kind of soon, kind of sort of.
For long and unsigned long, it's an insane amount of time, actually. That's like heat
know,
death
but
of the universe long.
Isn't it like 2040 when the epoch runs out?
For a
Depends on-
64-bit number, no.
Okay. Well, let's do a quick calculation.
It's not even
Let's see.
close.
Let's do a quick calculation. Let me start up the calculator. And let's look at what happens when, okay, so 1 shifted by 63 places. Is that the right, or should it be 64?
I'm pretty sure it's 63 minus 1
Yeah,
would be the
no,
max.
okay, I
Because
think
you have to,
it's
you need
63.
0.
Well, if it's a signed value, then you don't want to put anything into, this is an unsigned maximum value. Okay, so take that number. There are 60 seconds in a minute. There are 60 minutes in an hour. There are 24 hours in a day. There are 365 days in a year. There are, well, that's how many years until this is a problem. So can you trust me that it's not a problem?
I was thinking of the 32-bit.
Right, but that's already happened.
I thought 32-bit was in 2038.
No, it hasn't happened for the epoch, since the epoch. That will be in 2038. They even have a name for it. Y2K 38.
Well, there must have been other overflows because there's been overflows many times of Unix time. So, all right. Let's move on in my agenda. If there are no other questions. You understand Project 5?
Um,
Go ahead.
with SIMD, and the neon instruction set,
Yes?
I'm still a little confused, on the difference between the two.
Okay, say that again.
I'm still a little confused on like the single instruction multiple SIMD and the difference in neon.
Okay, so Neon is a brand name for SIMD instructions on the ARM.
Okay.
Okay, so Neon is just a brand name.
Okay.
So SIMD is the technology. So let's take a look at this example I did for you of the benefits of SIMD. So what I wanted to write in this example is a function to determine the Euclidean distance magnitude. And that's just x squared plus y squared plus z squared, let's say with w. So this is x, y, z, w. And if you wanted to use it as 3D, you just give w the fourth float as 0. And that's how you would get the magnitude of a 3 vector, 3 tuple. Okay, so it's just the square root of x squared times y squared times z squared, and here's w squared, which you don't have to use just by giving it a value of 0. Now, if you look at this, there's 1, 2, 3, 4 multiplies, and there are 3 additions. So if you look at the assembly language that corresponds to, you've got 4 loads. There's your 4 multiplies. Here's your 3 additions, and then your square root. Any questions on that? I'm not backing up any of the registers because I'm using only scratch registers and no function calls. All right, now in addition to that, you need to also count instructions because instructions are also memory fetches. So here there are 12 instructions. So is that right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, well, 13, including the return. But you have to have the return in both cases, SIMD or not, so I did not count it. Now let's take a look at the instructions that you would get by just looking at SIMD. So load What is X0? X0 has the pointer to an array of 4 floats. So in the non-SIMD, there's the first one, there's the second one, third one, and fourth one. Now, in the case of the SIMD, we load all 4 of them at once into a Q register. That's 4 floats. So a Q register has room for 4 floats, or 16 bytes. Now, the SIMD registers map over the Q registers, over the other registers, but they also give you the opportunity to specify a lane. So here, I'm going to multiply what's in V0, all 4 lanes of single precision, by V0, there's my square, all 4 lanes of single precision, putting them into all 4 lanes of single precision. So that is the SIMD multiply, floating point multiply. Then I'm going to run add pair twice. And that's pretty cool. You'll see why, because I broke down in the next few lines, I broke down what the register values are after each instruction.
So
Go ahead.
what exactly are the V and the S doing?
Okay, so the SIMD registers overlay over the floating point registers. So V0 refers to the same space as Q0. But the V registers allow you to break them apart into lanes. So you can have in the 16 bytes, you can do 16 calculations on char, or 8 calculations on shorts, or 4 calculations on ints or single precision floats, or 2 operations on longs or doubles in the same register. So it's a great picture to think about it as lanes. So in one V register, I'm using 4 lanes of float.
And this is done by passing the X0, loading it into the Q0 register. So that you
Right, so this loaded 4 floats.
yeah, those 4 offsets that were in the previous example loaded all of that, correct?
Correct.
Okay.
All right, let's take a look at what the input is. I chose this input so that you can see familiar numbers, and they'll all be different. So line 1 here, indicated by the 1 there, does the load. So now Q0 contains 1, 2, 3, 4. These are single precision floats. After the multiply of V0, all 4 single precision lanes, times V0, all 4 single precision lanes, put into V0, all 4 single precision lanes.
Well,
You
I have
get
a question.
squares. Yes?
You're loading from an X register though. How would you get
No, I'm not.
all 4 values? You said LDR Q0 X0.
That's
Don't
not
you
what I
need to-
wrote. Where do you see that?
Magnitude V LDR Q0 X0.
Wrong. That's not what I wrote. That's not
I'm
what this
confused.
says, Cephas.
Well, I mean,
What?
What is an X0? What is
An
X?
address. That's a dereference of X0.
There we are. Sorry, I get it.
Got it.
I'm good.
All right. So it's obvious what the value of the square should be. But now we have to sum the 4 values. So watch how it works. It's pretty cool. So we want to do this pairwise addition. And the way that it's going to work with 2 instances of add pair is 0 and 1. Think of this as the original 4 float array. 0 and 1 will be added together and put in 0 and 2. And 1 and 2 and 3 will be added together and put in 1 and 3. All at the same time. All right, so let's look. Here's the array index 0, array index 1, array index 2, array index 3. So into 0 and 1, you'll have the sum of 0 and 1. And notice it's also here, 0 and 1. That's 1 and 4 makes 5. And then in the next value, you have 9 and 16. So there's 25. God damn it. Who thought it was a good idea to make a double click, go back to the source code? Who thought of that?
I mean, I think it is sort of a good idea, right? Because you want to edit it.
No, okay, fine. So then the second invocation does the same thing. And notice 5 and 25 becomes 30. And 5 and 25 becomes 30. So now all of the lanes have 30 in it. But I did the sum of v sub 0 plus v sub 1 plus v sub 2 plus v sub 3 instead of 4 additions. I did it in 2 additions. And there's my total, 30. And then the 30 is sent to the square root function. Okay, so let's look at this code again. So there is an example of the benefit of SIMD.
Why is it that 4S?
So you're breaking apart the V0 register into 4 single precision floats.
Uh-huh.
The V0 register is in the same physical register as Q0. So all of the lanes in V0 are sitting in Q0, just not broken up into lanes.
So are there going to be problems with memory management as well? Because like, let's say you technically only have 2 lanes, but you're acting like there's 4. Would that overwrite values, or the opposite way around? You have 4 lanes, but you're acting like it's 2.
I'm sorry, Rebecca, can you repeat that? I'm not sure. I didn't understand you.
I was asking if there would be memory management problems. Well, more along the lines of I'm overwriting something I shouldn't. And so like I'm trying to access one part, but I accidentally destroy the whole thing or something along that line.
Well, remember, these are registers. There's no impact on memory.
Okay. Got it.
Okay. Now, what's different between this and the project that you're writing? Well, for one thing, this is a very small example, the magnitude, and it's returning to you a scalar, right? So you're handing it vector and you're getting back scalar. What does that mean? You're handing it multiple items of data and you're getting back a single number. Single number means scalar. Multiple numbers means vector. So in your project, you'll be working on vectors. vectors in, vectors out.
Is there any way to access or print or display a SIMD register?
Yes, there is. That's how I created this document.
How would one
Okay.
go about that?
Okay, well, you know how to display a register, right? So P space dollar
No, in
X zero.
C. Or
Oh. Yeah, well,
or
in
can we
C,
not do that?
it's just an array of float.
It's just, oh, okay.
Yeah, see, float 32 by 4 translates to float array of 4.
Nice.
Okay, so I thought you meant in the debugger, and the answer is yes, in the debugger you can do that too. Okay, so in the debugger you can print a V register, a Q register, whatever you want, if you're doing debugging. Okay, any questions? So what you're doing is timing the addition of two float vectors, summing pairwise into a third float vector. And then the check value is the sum of all of the values in the third array. Now, since the first arrays, A and B, are being filled with random floats, between 0 and 1, the average value is 0.5. So on average, adding 0.5 to 0.5 will be around 1. So your check value should be near the array size. Damn it. Now, this is the intrinsic. After all, that's what that's part of what this project is about, is using the intrinsics for the SIMD instructions. So this is the intrinsic that you're going to use. And it takes exactly you'll have to figure out how to use it. Okay? But it's going to take pointers. So the pointer for A is going to be an address. The pointer for B is going to be an address. And the pointer for C is going to be an address. And then it's going to do the right thing. The intrinsic will do the quote right thing. So you need to look this up to understand how to invoke it. Okay? So clicking here, you get to the document describing all of the instructions. And let's take a look at v_add_q, v_add_q, and what's the one that we want? What is it?
F32, as we
All right,
see
so-
in the preview of README.
F32. Okay, and the projection didn't follow me. So let me project again. Good. So here's the instruction. So the intrinsic takes a pointer to 4 floats and another pointer to 4 floats, and it returns 4 floats. Okay? So think of this as a small array, a small array, and a small array. Okay, you are ready to go on project 5. There was a question about threads. Can I hear that question again?
How do threads, like, what's the default processing power? Like, how can we tell
okay.
how much?
Yeah, so there's no, as I mentioned earlier, there's no predefined limit on how much of a processor a thread can consume. Okay? As far as the operating system is concerned, almost all the time, the operating system treats a thread as just like another process. What makes threads special and are in distinction from other processes is that threads share a virtual address space. So threads of a process are all living inside the same address space, inside the same memory. Compare that to multiple processes executing the same program. Well, sure, that means that the program is executing more than once simultaneously, but they're in different address spaces, so they're not sharing data unless you use some extraordinary way of sharing data, like pipes or network connections, shared memory. Okay? All right, so now it's time to introduce P6.
Sort of random. Do we actually have a networking course of any kind?
Yeah, we do. And it's a really good networking course.
Taught by
However,
you?
yes, it's taught by, of course, it's one of the hard courses.
Nice.
Well, I should say it's one of the systems courses, right? Now, systems code is just different from everybody else's code. Systems code is, deep, dark, dirty, get it done code.
Yeah.
All right. So among the faculty, I specialize in the deep, dark, and dirty. So put that on.
I was just about to do that.
Wait, is that a song or something?
No.
It's not? What does
Okay.
that mean?
So what? What does what mean?
No.
All right. So systems code, things like operating systems, things like the computer comp org, the networking course. Yeah. So anyway, Steve, if we do have a networking course, the last time I offered it, too few people signed up because they heard it was hard. People explain this to me. They heard it was hard, and people wonder, when will I ever use what you learn in this course? And of course, I get emails saying, I'm so glad that I took the networking course because I'm able to do networking, low-level networking code that none of my colleagues can do, and they're jealous, and I get paid 5 times more than they do, and they weep at night. Okay, so maybe someday I'll offer it again, but I was bitten. It's a big deal if your course doesn't have enough people enrolled. It causes a great deal of hardship, and I just don't want to do that again. That's why I haven't offered it recently. But it was a lot of
Are you
fun.
going to offer it at all?
It's not on next year's schedule either.
Wow, that's a rep.
Well, like I said, last time I offered it, only 2 or 3 students enrolled, and that was the end of it. It'll be a bunch more years before I offer it again. Okay, so let's take a look at project 6. That's not what I wanted. I wanted GitHub. And here, here. Okay, project 6. This one's a lot of fun. Students, we did not do this in operating system, did we? No, we didn't. Okay.
No.
All right, so there's going to be a demo and as well as a framework for your project. This project is assembly language, again. And there's an amazing amount of learning that you can get out of that function. Okay, that's memcopy. You tell it how many bytes you want to transfer, give it the address of the source, give it the address of the destination, and it copies from source to destination that many number of bytes. Boy, that is simple. How much learning can you possibly get from a function as simple as that? Turns out quite a bit. And in the demo program, I've implemented memcopy 6 different ways. Let's take a look at the first way. Yeah.
Oh, with you saying the word naive again, it reminded me of a question I was going to ask but forgot about.
Go ahead.
In the project description for what you want for the output, you mention a naive or native or whatever the heck for the output. And I'm wondering, where do we get the naive versus the check? And what's that supposed to be? Is that like the time or something else?
No, here. So, okay, so naive, Thomas, means the simple-minded approach. This is the time of 10 iterations on an array of 500 million. 50, how many? 50 million? Okay, on 2 cores. So the naive ran that fast. The neon instruction set ran that fast. They both must produce the same check value. That is your sign that you implemented the code probably correctly. And all the check is after your iterations are through, you've done all of the iterations, you're left with array C that has the sum, right? So the check, didn't I give the source code to the check?
The check is the sum with the getSum function. Yeah, you
Yeah,
did
getSum.
mention that.
Or is it sum of sums?
Sum of sums.
Right.
And that one we'd like sort through and treating the float pointer as if it was an array, correct?
Okay, no sorting.
No sort. I mean, look through the pointer as if it was an array to get at each of the individual
Exactly.
floats equal to size.
Right. So you start out at sum equals 0, and then treat C as an array, which it is, and just add up all the values in C. Okay, so it's a for loop where the current value is being summed or added to a variable. Okay, any questions on that? Okay. Going back to project 6, that's not what I wanted to do. So here are the 6 different ways of doing memcopy. This one is so naive, I didn't do it. So memcopy 1, which, forget about the 1, because I didn't even include this, does it 1 byte at a time. 1 byte at a time, and it uses a loop variable. Okay? So what could be more simple than that? Well, this one is the slowest. Let's now look at speeding it up. What's the difference between this one and this one? I claim that the second one is faster than the one that came before it.
You are when you're actually like copying over the entries, it's using the addresses directly rather than applying an offset from the beginning.
Exactly. So this version saves the computing of the offset. Okay. But it also includes a loop variable, which is pointless. So this is the next version. It also transfers 1 byte at a time, but it has no loop counter. Instead, it uses an address of the end of the source array as being the terminator. So just like in the previous example, I'm using the addresses directly. So the value in S starts out at the beginning of the source array and S keeps getting incremented until it reaches the end of the source array. And that's what E is. E is 1 position after the end of the source array. So while the address of S is less than the address of the next byte beyond the array, you keep going. Okay?
How is this faster?
No loop variable.
Ah.
I mean, look at it. I do a transfer, 1 piece of work, then a loop counter, 2 pieces of work. 50% of those 2 are waste. So this one's going to be a lot faster than that one. All right. Okay. So the next version, why transfer 1 byte at a time when I can transfer, let's say, 8 at a time using a long? Now this is a bit for bit copy. So if I treat a byte at a time, there's no difference. Byte at a time or a long at a time. I'm not doing anything with those bits. I'm just copying from one place to another. So I'm not interpreting the information in any way. So the only difference is I have to do some casting because now I'm working with pointers to longs instead of pointers to char. And I have to adjust how to calculate the end. And then after that, it's the same thing. I'm just moving 8 bytes at a time. This does put restrictions on your data because now your data has to be a multiple of the size of a long. It has to be a multiple of 8. Let's go faster still. I'm going to unroll. I'm going to keep the same approach, but I'm going to unroll it. So that way, I do 8 transfers per check of the end pointer. This is doing 1 transfer per check of the pointer. This one's doing 8 transfers per check of the pointer.
As you
Yes, yes.
mentioned, these put some restrictions on the actual data you can transfer.
Yes, that's right.
So like in general, I guess memcopy can't use these methods, right? Because it doesn't know the size or if it's even byte aligned of the data you're passing to it.
Okay, true. It doesn't know the byte alignment, but you can write code to detect the byte alignment.
But does memset have that? Does memcopy have the code implemented?
I invite you to find the source code to the Linux memcopy, and you will find that it is very sophisticated. Okay, memcopy itself implements multiple algorithms and calculates which one is the best for a given data set of circumstances.
How kind of it.
Nice.
Okay. Okay. So next, let's add threading. Now here's memcopy 4, and it takes source, destination, and size. So all I got to do to run this on 2 threads is launch memcopy 4, source and data, and half of the bytes. Launch another thread with the pointers being adjusted to halfway, and run it again on half the number of bytes. So if length was 10, then in the first case, you're starting at index 0, and in the second case, you're starting at index 5, and doing only the half the size of the full buffer. Does everybody get that? So this is how we broke a sequential algorithm into a parallelized algorithm. And this was particularly easy. Because we can divide up the data set, the data to be worked on, into multiple chunks, which I can work on independently. And when you have that opportunity, you should take advantage of it, because it's so easy to parallelize. The key idea is the different chunks can be worked on in isolation of each other. They don't mix their values. All right. So the program you're going to write, I give you a lot of the source code. The program you're going to write is the memcopy, but it has to be done in an optimal way, as fast as the processor architecture can support. And so you're going to have to do loop unrolling. You're going to have to do some really cool things, including your first time use of a jump table. So that's actually what this project is about, is doing address arithmetic on instructions and branching to the result of the calculation on instructions sizes and numbers. Okay, so I'm going to show you the world famous jump table. This is the duck device. Now it's written in the original C language. So line 1 here, this is the calling convention, the signature. It takes 3 arguments, but in the original C, the definition of the arguments come after. In the C and C++ that you use today, this would have said short star to, short star from, int count, and that would have been here. But in the original C, the definition of what the parameters are comes after. The word register is a keyword in the language, but we don't use it anymore. Because, well, what it did is it was a hint to the compiler to keep that variable in a register, rather than keeping the variable in memory. Now, when we tell an optimizer to just optimize, it'll do that automatically. It'll figure out what can be kept in the registers. All right, so here you have a switch statement embedded in a while in a do while. Look at that, you have case 0 do. All right, so Does this make sense to you? What does this do?
It makes 2 equal to the next thing in from.
Okay. Let me explain. Now, this isn't exactly a mem copy like you saw it before. Notice 2 is not being modified. You remember when I talked about memory mapped IO? So Tom Duff was a pioneer, is a pioneer in computer graphics. And think of 2 being the graphics hardware. So this is transferring the picture to the graphics hardware. So get a byte RGB, right? RGB. So get a byte, put it out to the device, get a byte, put it out to the device, get a byte, put it out to the device. Right, but so you got that part right, Thomas, but what else? This is the question that Cephas had. Does he recognize that this relates to the question that he had?
He is not entirely certain what question you're referring to.
Uh-huh. That's what I was going to say. Does he recognize which question I'm referring to?
He is not certain.
Well, didn't Cephas ask, doesn't this code that we showed before put constraints on the number of transfers you can make? And it's 8. What if it's not 8?
You're using the remainder function, so just go down to 0, between 0 and 8 again.
Okay, so let's try working through this code. Let's say the count is 1. You only want to do 1 transfer. Okay? So count is 1. And so 1 plus 7 is 8. Divided by 8 is 1. Taking count is 1, mod 8. That is going to be a value of 1. So n represents the number of times through the while loop. So you're only going to go through this once. But where you start in the while loop is determined by the remainder. So count, which is 1, mod 8 is 1. So I execute case 1. I do 1 transfer, and n has reached 0, and I'm done. Okay, so now the next interesting value will be 9. Right, so what if the count was a 9? 9 plus 7 is 16. Divided by 8 is 2. That means we're going to go through the while loop twice. But where are we going to launch into the while loop? Well, 9 mod 8 is 1. So the first time through the loop, we land here. We do 1 transfer. N goes from 2 to 1, still greater than 0. So we start back up here at the do, and we do 8 more transfers, summing to what? 9. N goes from 1 to 0, and we're done. Is that beautiful or what?
It's pretty nice, not gonna lie.
What? Okay, now think of this as a jump table where when you have to calculate how many instructions into the jump table, jumping into it, you should begin. And when you have, let's say, oh, I don't know, unrolled 8 sums for your, what does this project do? Forget. Oh yeah, memcopy. Got it. I got sidetracked there. So let's say you have 9 transfers to do. You do the odd amount first by launching into the middle of your code. So this is going to be a branch into the middle of your code. You have to treat your lines of code as addresses and do math on them. So the first time through the loop, you pick up the strays, and then what remains is some number of full calculations through the loop. So if it was a 9, count was a 9, you do the stray 1 first, and then a whole loop of 8.
So why, I'm confused about why you do the count plus 7 divided by 8. Like, I understand you want to make sure that it's divisible by 8, but what if it's already divisible by 8? Adding 7 would just be unnecessary.
You sure about that?
No, not at all.
Okay, so let's put it in. If the count was 8, you'd 8 plus 7 is 15. Integer divide by 8 is 1. So n equals count plus 7 divided by 8, integer divided by 8, is telling you the number of times through the loop.
Oh. Okay. Yeah.
So if it were 8, you're going to go through a loop of 8 unrollings once.
That makes sense.
Okay, so behold the wonder of the Duff device. You're going to be creating something like this.
The what? You keep on saying that word and I don't understand it.
D-U-F-F, it's a man's name.
Duff. Oh, okay.
Tom Duff. Okay. All right. So let's take a look now at the code that you're given. So this is your framework. Here's getopt, the options that you have to specify to create. All right, now dash I followed by a number will be the number of iterations to time. Dash little l followed by a number is the number of bytes to copy. That's just like, but different from capital L, which computes the number of bytes to copy by shifting 1 up the number that you specified. So for example, dash capital L 10 would equate to moving 1024 bytes. Because 1 shifted over 10 times is 1024. Okay? The indentation is truly screwed here. Don't worry about it though. It shouldn't be screwed in the real text. Well, let's take a look. Let's look at raw. Yeah, okay. So the indentation is correct in the code. Don't worry about it. Here is another way of doing high resolution time, and that is using Chrono. Let's go up to the top. You have to include Chrono. And then you've got all sorts of really great tools for working with time. And this is platform agnostic. It's built into modern C++. Here is a reasonable use of a type def. Many of you have probably never seen the type def before. Is that true? Okay, who hasn't seen typedef before? Okay, so what typedef does is it allows you to rename types. So I don't want to have to type duration, blah, 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 double, blah, 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 as many times as I need to. So instead, I'm giving a name, capital letters duration means that. Okay? So it's like, kind of think of it as a different way of creating types out of existing types. Okay. All right. So the memory that's going to be copied is just going to be filled with random bytes. And then at the end of the copy, at the end of all of your iterations, you'll compare the source to the destination to make sure that it was copied correctly. Okay, nothing exotic here. All right. So I want to make sure it's an aligned alloc. And if the length is less than 16, round it up to 16. Okay.
And we will have to implement all of this in assembly, yeah?
No. This is given to you. The only thing that you're writing is memcopy.
I will be honest, I was panicking that entire time.
Okay. All right. You feel better now?
Much better.
Okay, but chief on my mind is how does Thomas feel? Okay. Okay, so the only thing that you're writing is this. But you've got to do it in this optimal way. Right? So I was telling you about this C++ style of timing. So high resolution clock. And I want to use it to collect points in time. And I have two of them, start time and end time. So high resolution clock now goes into the start time. You do all of your iterations, and then you've got high resolution clock now in the end time. So compute an elapsed time using duration cast with my typedef, end time minus start time. And then what's left is a double that is returned to you by count. So that would be like, 6.7125 sections. But you have to make it into an average. And then figure out from there how many bytes per second you're actually transferring. Okay? So I'm going to show you this running on my ARM emulator. And it's not pretty. Okay. So where am I? I want to be in P6. Do I have P6 here? No, I don't. So let me go, just wait for a second and I will squirt P6 over. P6. Okay, there it is. And maybe I'll show you how I'm squirting it over. Resume share. What do you see now? You don't see it yet. So what the heck? Stop the share. That's dumb. It's being thrown off by it being in different tabs. Okay. So SSH. Nope, that's not right. SFTP. Put in the password and put recursive P6. Where am I? local PWD, local LS. Oops, I don't have it here. So that means be quicker if I do this. PK mem copy asm. Yeah, okay. SFTP. No, wait. Okay, so SFTP to the ARM machine. Put in the password. Make a directory called P6, and then put star and quit. Now, if I go back, which I have to stop the share and share again, just because I'm going through different windows, different tabs. Okay, so now, whoops, I forgot to put it in the P6 directory. So move star to P6. And what did that do? Good. Okay, so G++, I'll optimize it to the hilt, main.cpp and memcopy.s. Oh, okay. Now, is this going to fail? Do I need to do this on the Mac? Because the two platforms, yeah, sorry, the two platforms are not compatible. So I wanted to see how fast it was on my M1 Mac, and that's why I'm now kind of screwed. Okay, so it only runs on the Mac now. Sorry. G++, main.cpp and memcopy.s. And a.out. And let's give it -s, 100,000. And we'll do it 100 times. Whoops. Oh, it's -l, lowercase l. All right, so this ran at 6.9 gigabytes per second, which is not really fast. So let me try building it again, but this time with the optimizer on. -03. And let me run the same thing. Well, now it's running at 13 gigabytes per second. Well, let's give it something really bigger to work on. So how about
3.
that -l, and here is 1 million bytes. Okay, up to 16 gigabytes per second. Let's give it 16 million bytes. That's 2 to the 24th. Okay, now we're at 17 gigabytes per second because it's got some reasonable work to do. Now, I'll guarantee you, if I ran this on the local ARM machine, it would not be that fast. But I've just demonstrated the program to you, okay? So what the hell, let's do 1 billion bytes, a gigabyte, L30. Now, what's taking time here is swapping. Because when you see the actual timing, you'll see that it's actually quite small. So the average time through the loop to transfer a gigabyte was 0.059 seconds. And that works out to 16.8 gigabytes per second. Now the full memory bandwidth of the computer I'm demonstrating with is about 60 gigabytes per second. So this code running at 16 says, if I added a second thread, I should be able to go 32 gigabytes per second. And if I added 4 threads, I should be able to get to all 60 gigabytes per second. But if I had 8 threads, it's not going to go any faster. Because I will have reached the saturation point of main memory. All right, who's got questions about this project? And the class is over, by the way.
I've got chills.
Chills meaning you're excited to do it?
They're multiplying. Yep.
He's losing control.
I feel
All
like
right.
I'm losing control.
But the
All
power
right.
you're applying is electrifying.
This guy gets it.
I'm sorry, I didn't get it at all. You're excited at the prospect of doing this. Is
It's
that-
a song, you know?
Okay.
I got chills.
All
They're
right.
multiplying.
Well, class is over. If you have questions, let me know. There will be a barbecue tonight in that I'll be there. If you're there, I'll talk to you. If not, I won't talk to you. Okay, bye-bye.